So we tried to establish a relationship between the pressure strain rate to this Reynolds stresses and the mean strain rate, and that's how the link came in the IP model. Okay, let's get started again. So last class we looked at the IP model or the pi ij rapid model, right? So the slow term is still remaining, and if you recall, we tried to establish relationship between the pressure strain rate with the known terms, which is the mean strain rate, right? So the knowns were have access to the mean strain rate. Okay, I have access to the Reynolds stresses itself and the dissipation rate. These are the knowns, and we linked the pressure strain rate rapid term to these two. The IP model is essentially linking mean strain and the Reynolds stresses, and the only term where these two terms are appearing together is your production rate terms. So the IP model has Pij, right? So if you just recall, the IP model was pi ij rapid was minus C2 rho Pij minus 2/3 Pk delta Ij. Model here. Now the slow term has to be modeled, right? So we look at pi ij slow term. Okay. So the slow term, if you recall, this was only a function of terms which were only had turbulent terms. It had no mean strain, right? So here there were no mean strain terms. In the pi ij slow. So it was entirely depending on correlations of fluctuations, right? So here there may be more than one approach how to model this. So I am going to follow one particular approach here. There may be another approach in some literature you will see. So we will go ahead with what is called in the modeling part, right? So we are going to model this term. So we will take up what I call, or what is commonly called as, physical modeling of pi ij or pi ij. There is no comma here, right? It's a tensor pi ij slow term. This particular model has a reference. It is also called Rotta's model. It's also called return to isotropy concept or model. Return to isotropy model. As we know, pressure strain rate takes away turbulence in a direction where it is produced and tries to give it out to the directions where it is not produced. So it is trying to make the turbulence isotropic, but it will not be, because there are other terms active, the production rate terms, the dissipation rate terms. So they will cause the unbalance between the three components of the stresses. So here what we do is, first we are going to take, I am going to consider now a point here, let us call it O, and then I am going to say, okay, there are two fluid particles here with, I will take two fluid particles. These two fluid particles now are bouncing against each other, okay. So this is, both are bouncing against each other and they are carrying a fluctuation u1 prime, and I will have this coordinate like this. This is x1, this is x2 coordinate. Okay, two fluid particles of u1 prime fluctuation bouncing against each other at point O. Okay, they want to collide here. So if this occurs, obviously the pressure at the point O will rise, right? The pressure fluctuation P prime will rise when these two will try to collide at point O. So we will use this concept to see what we can do it. So the first thing I would like to uh, argue model arguments is that now let two fluid particles with u1 prime bounce into each other at point O. When this occurs, so now look here, so you have here you have higher turbulence fluctuation, the zone here I am talking about, and same thing here, u1 prime high. When it collides, you will have a lower u1 prime fluctuation, right, at the collision zone. So this will be u1 low at the collision. So what will happen to the gradient dou u1 prime by dou x1? Dou u1 prime by dou x1. What will happen to this? Is it positive, negative? Negative, right? So this is negative. When this collision occurs, this gradient will be negative. Okay, let's call this 1. So as a consequence of this collision, as I already said, the pressure P prime should increase. As a consequence, P prime increases at point O. Okay. So therefore, since dou n prime by dou x1 is already negative, P prime being large is okay, but the entire part will be still negative. U1 prime, this part is already negative, right? So therefore, P prime dou u1 prime by dou x1 is taking a negative value here. All right. So now I'll make another argument that if when locally the pressure fluctuation is higher at point O and you are trying to bring two particles bounce against it, that means work is done against this pressure gradient, right? So that means the kinetic energy that is lost along the x1 direction must be transferred to the other two directions. That is what we are going in that direction. The pressure strain rate is doing this. So therefore, in x1 direction, work is done moving fluid particles against the pressure gradient. So this implies that the kinetic energy lost along the x1 direction must be transferred to the x2 and x3 direction. Therefore, the turbulence kinetic energy lost along x1 direction is transferred to x2 and x3 directions. So from 1, what will I get? Therefore, from equation 1, what do I get? If this is negative, the dou u2 prime by dou x2 and dou u3 prime by dou x3 is positive, also by continuity, right? So dou u2 prime by dou x2 is positive, dou u3 prime by dou x3 is positive. You can also say also from continuity. Okay. So now for this to happen, the kinetic energy, as I said, in the x1 direction should be larger than the other two direction, right? The kinetic energy lost along x1 is transferred to the other two, means the kinetic energy along the x1 should be larger. The TKE has to be larger compared to x2 and x3 directions, right? So for this to happen, TKE along x1 direction should be greater than, or I can write symbolically, should be greater than, use another color here, should be greater than TKE along x2 comma x3 directions. Okay, and this implies your u1 prime square average must be greater than u2 prime square average, and u1 prime square average must be greater than u3 prime square average. Okay. And another argument is that now if this the amount of energy that is being transferred from one to the other two directions should also be proportional to the difference in the TKE components. So we will try to establish now relationship between this particular stresses, or these three normal stresses constitute the components of turbulence kinetic energy, and we already have this pressure strain rate term like P prime by rho dou u1 prime by dou xn is one of the component. So we have to establish a relationship between this particular component to the TKE components. Okay. So we say now that the amount of kinetic energy transferred from x1 to x2 comma x3 directions must be proportional to the difference in the TKE components. What does this mean is I have P prime by rho dou u1 prime by dou x1 average. This should be proportional to the difference, that is half of your u1 prime square minus u2 prime square plus u1 prime square minus u3 prime square. I am relating this to the difference between the components in the TKE, right. So what does this imply is that I have now, so we are achieving the model here. So I would get essentially half of, or if I sum it up, I get u1 prime square minus half u2 prime square plus u3 prime square. Now I am going to add and subtract the other component, that is plus, so I am adding here plus half u1 prime square minus half u1 prime square. I am adding that because I would like to get turbulence kinetic energy recovered in the bracketed term. So what will this give is, I get 3 half u1 prime square minus half of u1 prime square plus u2 prime square plus u3 prime square. So this gives me 3 half u1 prime square minus k. So this is sufficient for one of the normal stresses, but we need a generic expression because the pressure strain rate itself is will have the other components, right? So there are 6 stress components. This is sufficient for one of the normal stress components. So we need a generic expression for shear stress as well as other stress components, right? So here, if you notice here, there will be a time scale missing. If I look at the dimensions for this, there will be a time scale must be missing here. That's what we will introduce later. So this will come as, I mean, you can easily see that the unit will be here only meter square per second square, but on the left hand side it should be meter square per second cube, correct? This should be meter square per second cube. So a time scale that we are familiar in Eddy-Viscosity models, the epsilon by k or k by epsilon, that part will appear in the model in a generic expression. Okay, so here you can say that this is applicable, this is applicable only to a normal stress. So we need a generic expression. Therefore, in generic form, the model will look like pi ij slow will be minus C1 rho epsilon by k coming for the time scale part, and the Reynolds stresses, which is ui prime uj prime average minus 2/3 k delta ij. So this is your pi ij slow term model. This should of course be used together with pi ij rapid, the IP model. So the pressure strain rate will have two components, pi ij rapid, pi ij slow. So both the models should be taken. The sum total has to be taken when you implement it. Okay, the IP model plus Rotta's model. There may be other options. I am just giving you an illustration of how the models are coming out, that is relating the unknowns to the known. There are other possibilities. It is not just that you have to use IP and Rotta model, but these are popular models. There are other models as well. But somehow we have to establish only links to what is known, and known is only Reynolds stresses, mean strain rate and dissipation rate of K. This is what is known. So it will be some form of only this, nothing more. Okay. So this will complete the only the pressure strain rate term, the rapid and the slow part. But now we have to also have an option, like just eddy viscosity model, we had option to resolve the flow all the way to y plus equal to 1. We also had options for wall functions. Similarly, you can do it here. If you are going to resolve all the way to the flow, all the way to the wall, then you need some wall correction terms here. Okay. So that will be addition of sum of two more terms. So pi ij rapid plus pi ij rapid wall correction term plus pi ij slow plus pi ij slow wall correction term. Okay, it will go like that. So we will see what these wall correction terms are. This is clear so far. The modeling, the slow term and the rapid term. Okay, there are, as I said, different models will have a slightly different approach. These two are what I am giving a flavor of how it is modeled, this particular term. Okay, so we look at, sorry, I'll give you all the model constants at the end, okay, because more model constants will come now in the wall correction and everything. I'll give you all model constants at the end.